Hi everyone and welcome to my YouTube channel. So it's been a long time since our last video in this functional equation tutorial, but that was mainly because I had many exams in my university and luckily now I have finished them. So let's return to what we have stopped at. Okay, so basically I promised you that we were going to talk about Cauchy's functional equation. Okay, so Cauchy's functional equations are very famous equations that you sometimes, when you are solving some functional equations, you reach such a functional equation. So for example, you prove that your function f satisfies one of Cauchy's functional equations, which is the additive one. This f of x plus y is equal to f of x plus f of y. And when you do this, when you prove that your function f satisfies one of Cauchy's functional equations, then you are done and you can immediately write the solution to Cauchy's functional equations. So that is basically the importance of Cauchy's functional equations. So in this video, we'll be discussing one of Cauchy's functional equations, which is the additive one, this one. And in the second video, we'll discuss the other types and how can we prove them in a similar way to the way that we're going to demonstrate today. Okay, so what are we waiting for? Let's get started. Okay, so the functional equation that we'll be discussing today is the following. Find all functions f from q to q, that is from rational numbers to rational numbers, such that we have the following simple functional equation: f of x plus y is equal to f of x plus f of y. Okay, and we need to solve this. So the first step is just like we are used to doing, and that is substituting with small numbers. So let's start by substituting 0, 0, because if we substituted 0, 0, we're going to get f of 0 is equal to 2 times f of 0, and that means that f of 0 equals 0. Okay, so that is a nice result. So first of all, we'll begin by p0, 0, and that tells us that the value of f of 0 is simply 0. Great. Okay. So what next? Well, take a look at this functional equation and try to understand it. This actually tells you that f of the sum of any two numbers is equal to the sum of f's, right, of the two numbers. So f of x plus y is equal to the f of x plus f of y. Well, if we substituted x the same value as y, that is pxx, we're going to get f of 2 times x is equal to 2 times f of x, right? So actually, let's do this. Pxx, that results f of 2 times x is equal to 2 times f of x. So in this way, we can find the value of f of 2 times x using the value of f of x, right? Okay, but what about f of 3 times x? Can we do the same thing? Well, yes, we can. Here we have f of x plus y. If we substitute y with 2 times x, we're going to get f of 3 times x is equal to f of x plus f of 2 times x. But f of 2 times x is 2 times f of x. So we are going to get the same result, which is f of 3 times x is equal to 3 times f of x. And from here you can immediately notice that if we can show that f of 2 times x is equal to 2 times f of x and f of 3x is equal to 3 f of x, then what about the generalization? Can we show that f of n x is equal to n times f of x? Can we show that for natural numbers? N? Well, yes, we can. We can do just the same way. So we can prove this using induction. So our result is true for f of 2x. We can assume that f of kx is equal to k f of x and show the result for k plus 1. And this is very simple. We can simply just substitute p x kx. Of course, we are assuming that the result is true for k, for n equals k. That means simply that f of k plus 1 times x is equal to f of x plus f of kx, which is k times f of x. So this is simply k plus 1 times f of x. And indeed, our induction is right, is correct. That means that the result is true. So we have now f of nx is equal to n times f of x. So actually, let's write that down instead of writing all of this. So okay, so now our second result is f of nx is equal to n times f of x for all natural numbers n. Okay, great. Well, this is true for natural numbers, right? But not for integers, not necessarily for integers. So for negative values, we're not sure yet. But actually, we can show it for integers as well. And that's very simple. Because we know the value of f of 0, which is 0, we can here simply, that will motivate us to substitute y with minus x, right? So if we substituted y with minus x, so we're going to get f of 0, which is 0. 0 is equal to f of x plus f of minus x, and that means that f is odd. So why not adding this to our results? That means that f is odd. And because f is odd, then we can actually show this for negative values, or that means for integers as well. So actually we can now, instead of writing n, we can write z. Great. And of course we know that f is odd. Okay, now actually take a look at this result. F of nx is equal to n times f of x. Actually, this is really powerful. And remember that our functional equation is not from R to R, it is from Q to Q. So does that tell you anything? You have f of nx is equal to n times f of x, and n is any integer. Well, actually, we have already found the value of f over all integers. Why is that? Well, just substitute x with 1, and you're going to get f of n is equal to n times f of 1. But f of n covers all integers, so f of n is the f of any integer, and that is n times f of 1. We can assume that f of 1 is just a constant c, and get that f of n equals nc. Okay, so actually let's write that. So basically, by substituting here x with 1, we're going to get that f of n is simply n times c, where c is f of 1. So we can here write c is f of 1. Okay, great. And this holds for all integers, right? So if our problem was from z to z, then we are done. But it is q to q, from q to q. Okay, so can we maybe make a small trick to solve the issue? Can we generalize from z to z into from q to q, depending on this functional equation? Well, yes, we can. In the same way that we solved it for integers, we can do the same here. So previously we substituted x with 1. But what about using this to show it, this x, the same x, to show it for rational numbers? Well, just substitute x with a rational number. So the idea is this f of n x is linked to f of x, right? So if I can find the value of one, I can find the value of the other. So here f of x, by substituting x with a rational number, this will be f of rational number which we want to evaluate. But this we can make it an integer. How can we do this? Well, this is very simple. Substitute x with a rational number, m over n. So n will cancel n, and you will get f of m, which is an integer. Great. So we will be basically done. So just substitute x with m over n. We know that all rational numbers can be represented as m over n. So that means that f of m is equal to n times f of m over n. But we already know the value of f of m because m is integer, right? So it is mc. So that means that mc equals n times f of m over n. And of course that means that f of m over n is equal to m over n times c. So you can see that it still holds. So f of x is equal to xc. So basically this is our solution, because we are already done, because our problem is from q to q. So the function is f of x is equal to x times c for some constant c, any constant c. Of course, c should belong to or should be a rational number. So for any rational number c. And we are done. Now we just need to check that indeed the functional equation holds, or that our function f is a solution, which is very simple. X plus y times c is xc plus yc, and this is very simple. So indeed we are done. Okay, so this way we can show or solve the first Cauchy's functional equation, the additive one. Whenever you have a function that satisfies this equation, then you can say that f of x is equal to xc. But the problem is you need your function to be from q to q. Great. So far we have solved the first Cauchy's functional equation, f of x plus y is equal to f of x plus f of y, on rational numbers, so from q to q. But I know what you are saying right now. Cauchy's functional equation is awesome, but the problem is it is from q to q. And nearly, I think, all the problems that we have solved before were from r to r. So it should be pretty useless, right? Because if I know the values from q to q, why is that useful? Because I need to solve it from r to r. And here is the cool thing. Actually, you can solve it from r to r, but you need to prove some conditions. And actually, there are many conditions that you can show in order to generalize the statement for real numbers as well. And we'll just talk about two of them, the most famous two. Actually, if you can show that your function f is increasing or decreasing, then you are done. You can actually generalize. So if you can show that f is increasing, then you can say that f of x equals c times x is the solution. And the second condition that you can show is f is continuous. So for example, if I tell you that solve this functional equation given that f is continuous, then you immediately say that f of x equals c times x for real numbers as well. Okay, but why is that? Why is that true? Why is the increasing condition that important? Well, actually, let's find out. So let's actually just add one condition, that is f is increasing. And of course you can discuss the decreasing one in the same way. So let's actually add this condition. This is the first one and this is the second one. Okay, now actually we will prove this by contradiction. So let's assume that our function f is in Cx for some numbers. So actually, first of all, let's define the function g of x, just for simplicity, that is equal to f of x over c. We know that f of x, actually we can just write c as f of 1, so where c is f of 1, and define the following function, g of x equals f of x over c, or f of 1, and then we can actually solve the following problem. Okay, so g of x is still increasing or decreasing depending on c, right? So if c is positive or negative. Okay, great. So now let's work on with g of x. So now we know from our previous work that g of x is equal to x, right? For all rational numbers. So the first result we can say is g of x is equal to x for all rational x. So we know this, but we need to generalize over R, right? Okay. So let's actually prove this by contradiction. So let's assume that there is some value t that is a real number. Of course, it's a real number, not a rational number. And that satisfies g of t isn't equal to t. Well, if it is not equal to t, then we have two cases. It is either greater than t or less than t. Let's pick up one of them. Let's assume that g of t is greater than t, and we can show it in the same way for the second case. So let's actually assume that g of t is greater than t. Okay. Of course, g of t is greater than t. Well, here is the cool idea. You know that g of t is strictly greater than t. But I want to ask you a question. Can I find one rational number r such that r is less than g of t and r is greater than t? So basically here we have two real numbers, right? Two distinct real numbers. Can I find one rational number between them? So actually the answer is yes, because between any two distinct real numbers you have always one rational number. Actually lots of rational numbers, but let's pick up one of them. Let's call it r. So basically let's assume that r is a rational number. Of course we have such a rational number, and that satisfies r is between t and g of t. Okay, why is this important? Well, remember we have the condition that f is increasing, right? So since r is greater than t, be careful, because r is greater than t, so we know that r is greater than t, and f is increasing, that means g is increasing as well, or maybe decreasing, but we can discuss it in the same way. So if r is greater than t, that means that g of r is greater than g of t, right? But g of r is r, so that means r is greater than g of t. But take a look here, gt is greater than r, and we have just proven that r is greater than g of t, which is a contradiction, and that's why our statement is wrong. So we cannot have such a t that satisfies g of t is not equal to t. That means g of x is indeed equal to x for all real numbers, and that means that indeed the increasing condition is really powerful and it solves the problem. So as a conclusion, when you are solving a functional equation and you have proven that your function f satisfies the additive Cauchy functional equation, that is f of x plus y is equal to f of x plus f of y, and if your problem was from rational numbers to rational numbers, then you are done. You can immediately say that f of x is equal to c times x. But if you are solving it with real numbers, then you need to show one more condition, and that is show that f is increasing, or f is decreasing, or f is continuous. And of course, there are other conditions as well, but these are the three most important ones. And when you can show one of them, then you are done. You can say that f of x is equal to c times x for some constant c. Okay, so that was our first Cauchy's functional equation, and in the second, or in the next video, we'll be discussing the other Cauchy functional equations. So if you like the video, like, share and subscribe to the channel, and see you guys in the next lesson.